Okay. This is going to be probably a dense lecture, so my suggestion might be to download the notes, maybe just listen the first time. And then after we talk about this a little bit in class, maybe listen to it again and take more notes on what we talked about. This is something where we now have to venture back into calculus. And some of the ideas of calculus I think are quite challenging, especially at the freshman level, especially if you are concurrently taking Calc 1 while we are doing this. On top of that, a math course kind of teaches the ideas of calculus in a very certain way, where, of course, here we want to have some physical intuition about what's going on and what calculus actually is saying and why it is relevant in order to describe these sorts of physics problems. So my hope with this is to try to give some kind of conceptual motivation behind the derivative and the integral. And this will be less about me actually doing integrals and doing derivatives. That's just technique that can be learned, that can be practiced. Here we're trying to develop a conceptual understanding. And I think this topic might be a decent one to try to do it with. The idea here of we've now been focusing on calculating the electric fields for single point charges. We've done electric fields now of a few point charges, like the dipole, where the net electric field then is just the sum of the electric fields from all the individual components. And if you have 2 or 3 point charges, that's not too bad. But when you have 100, 1,000, 10 to the 6, you probably do not want to kind of brute force start adding up each of those individually. We have to start thinking about kind of what we might be able to do, particularly as n gets huge in this case, where you have 10 to the 6 charges or 10 to the 20 charges. So what we are going to do is we're going to approximate the distribution as a continuum, rather than, though we know that charges come in individualized discrete packets. Right, there's fundamental charge units that charge comes in. This treating things as a continuum is going to be a very powerful, very accurate approximation for what's actually going on. But the kind of fact that we are dealing with something, like these charges, where charges are actually discrete little things that you can count, that is at least a little bit easier to wrap our minds around. So we're going to hopefully use that to develop some ideas about what calculus is trying to do, which is dealing with something that is kind of smeared out into a continuum. So here's some motivation. Let's consider a 1D rod. Now, what does it mean to be 1D? Nothing is truly 1D. 1D, what I mean by that is it's going to be extremely thin in all but one direction. So, right, it might have some length along the x direction, but be essentially, infinitesimally small in the y, infinitesimally small in the z, like a thin wire. We're going to effectively treat that as a 1D rod. It has length L. And charge can be spread out on the rod in some possible way. So if this is the rod itself, right, there might be kind of bunches of charges built up over here, and maybe some charges here, and maybe not as many over here. So this would be an example of a non-uniform distribution, or I could have all the pluses kind of uniformly spread throughout. That would be a uniform distribution. And, in this case, what if there are 10 to the 6 of these little things? And I'm curious to know, say, what the electric field is at some point away from the rod. So if there were only a couple charges, of course, I could calculate the E field from this one, and then this one, and this one, this one, and then add up all the vectors. But that, of course, gets ridiculous as you get to more and more of these things. So at some point, again, it becomes impractical to kind of do the kind of brute force discrete way of doing it individually and adding them all up. We need some other method. We need some way of both efficiently doing this, and we want, of course, this to be an accurate approximation. If we are making an approximation, of course, we want it to be accurate. Or if we can convince ourselves that we are actually getting the true right answer, then that's great too. And ideally, it's efficient in that we can do it in some meaningful way, and you're not sitting there calculating 10 to the 6 vectors to add together. So to do this, in thinking about things, on a continuum, let's just think about charge. We're going to set E fields aside, essentially, for the rest of this lecture. We'll come back to those in the next lecture. Let's just think about the charges themselves and what it means to think of the charge distributed on a continuum. So we can think of this more as an experimentalist, or someone who's trying to model something. So if I told you that if I have a rod of length L, and I told you there's a total charge Q on that rod, and that's all you knew, I could tell you nothing else. What is the most kind of fairest, accurate way that you can represent the charge on that rod? You know there's a charge Q, you know the rod is length L, I tell you absolutely no additional information. Well, then the fairest representation is to assume that that charge is kind of uniformly spread out over the rod. So again, let me draw it down below. All right, so if I have some rod L, the fairest thing to do is assume that the charge is kind of uniformly spread out. Now, why is that the case? Why is that the fairest way of assuming things? Because if I said that the rod had a length L and a charge Q, and I knew no other information, but you said, well, actually, I'm kind of convinced that all the charge is over here. Well, then you actually know more information than what you claim. Even though you have Q, a charge Q and a rod of length L, you know additionally that the stuff is kind of packed over, onto the side, with length, called little l, that's smaller than L. So if you're stating that your ignorance kind of is that you have a rod of length L and a total charge Q, and that's all you know, then that's essentially saying something about the resolution of your information. That on scales that are smaller than L, if you were to zoom in, you do not have any information that allows you to kind of zoom in beyond L. L is kind of your smallest pixel. If you think of this like an image. If you zoom in enough on an image, right, you can eventually see the individual pixels. The individual pixels are just usually all a single color because there's no additional information that you can go beyond within a pixel. If you could, then you could break that pixel into smaller pixels, and that would give you kind of more information on smaller scales. So this rod of length L, if all I know is that it's a charge Q, then essentially this is my pixel, and it's kind of biased and unfair for me to assume anything other than that the charge is kind of uniformly spread out within. Because again, if I had this case on the right, really I'm claiming that my kind of resolution is little l, and I would have kind of pixels like this, and I would be able to say something about how the charge is distributed. In that case, I could say something about what's going on over little l. So if we think about that, and if the kind of thinking of things over like a resolution of L is confusing, then maybe think of it like a bucket. Like the pixel is kind of the basic idea of what I'm trying to go for here. Like if I said that if you had one bucket and there was a charge Q kind of within that bucket, and that's all you knew, the fairest thing to say is that you can say that there's Q kind of within this bucket, but where all those individual charges are located is anyone's guess. So you might assume that they're kind of randomly located or uniformly kind of like spread out in the bucket. And that's different than if you were to say like, let me actually draw that down here in the space. All right, so if I had one big bucket, and let me make a couple copies of this. And I had a bunch of charges Q. And again, all I knew is that they were kind of within this single bucket. So only looking at the one on the left. So kind of Q within a single bucket, right? So Q is essentially anywhere within this bucket. But then if I realized that my bucket actually was two buckets, those aren't really the same size bucket, but go with me here. Then essentially if I actually have two smaller buckets instead, Then I can say something about kind of that there's, let's see, how many dots did I put? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there are nine little dots. So, all right, looks like what I'm saying is that kind of 6/9 of Q is actually over here on the left, where 3/9 of Q is over here on the right. So I can say something more about kind of where the charge is based on that resolution. And then again, if I have 3 buckets, then it looks like I can say 2/9 of Q is here, 4/9 of Q is here, 3/9 of Q is there. Which again, I'm able to say something a little bit more about where the charge is located. In this first case, it's anyone's guess kind of where it is within the entire bucket. Here, it seems like I'm saying that there's kind of more charge kind of lumped over it on the left side compared to the right side. And then here, it's saying that, well, yeah, there is more on the left, but actually it seems like there's kind of, the mode is more, there's more in the middle compared to on the left and on the right. So it's kind of a distribution kind of in the middle versus, what these are saying. So again, the finer the bucket, the more we know about the individual charges and where they exactly are. And you can imagine I could keep going, instead of 3 buckets, 20 buckets, 1,000,000 buckets, 10 to the 9 buckets. Eventually, your buckets are going to get small enough that you can actually start to put only a single charge in a particular bucket. The charges, right, if we take these to be like atoms, then that's on order like 10 to the minus 10. If I have enough buckets so that, if my bucket size is on order, say, 10 to the minus 10, or I have 10 to the 10 buckets, within a meter or so, then I could conceivably put each individual charge only inside a single bucket. And even then, I don't know the exact location of the individual charges. I would only know kind of that, if I knew a charge was in a particular bucket, then I know that charge is within, some position that's kind of, again, if the bucket's kind of 10 to the minus 10 meters, long, that the exact position of that charge is, known to within plus or minus, 1/2 times 10 to the minus 10 or something like that. Because I only know kind of down to my pixel size or my bucket size in this case. So there's always essentially some approximation going on when we're talking about the locations and things. And I'm not even going to bring in things like quantum mechanics and the fact that all these things are kind of vibrating and moving around. Right? I'm just talking about the just idea of measurements. As we kind of think about measuring these things, there's always going to be some resolution that we are resolving these things on. Essentially, how big are my buckets? That I can narrow things down to. So, if I wanted to talk about how much charge, if I go back to the idea of a rod, so I have a long rod and there's some amount of charge on the rod, and I want to describe how the charge is distributed on the rod, then, and I don't want to write down X, Y, Z coordinates for each individual charge, but want to say more about how it's distributed. Is there more charge to the left, to the right, etc.? Then I can think of this, essentially what I'm doing is I'm calculating essentially an average that, if I go back up here to these, here, like over this entire, distance here, the average charge per size of this bucket is given by the charge divided by this length. In this case, then the average amount of charge per this length, gives me kind of how much charge is over here compared to how much charge is over here, and then so forth and so forth. So we can talk about instead a 1D charge density. So this density is saying, again, not about where individual charges are, but kind of telling you about the average kind of spread. So it is, I'll use lambda for the 1D density, and it has units of, again, charge per length, with the idea of, how much charge is in, a given length, where, like this bucket here, there's this amount of charge within this length. And beyond that, it's anyone's guess at kind of where it is, but that's just telling me kind of the detail within that kind of resolution. So again, if I say that there's a charge density of 3 nanocoulombs per meter, and that's all I knew, then what this says is that within a meter, if I had a rod that was 1 meter long, that there are 3 nanocoulombs distributed along that rod. Where on that rod? I don't know. I need more information to say beyond this. But this is saying essentially 3 nanocoulombs spread over 1 meter. And those charges are kind of anyone's guess, but again, the fairest way to represent that is to treat it as if it was kind of evenly spread out over that meter, pending more info, of course. Of course, we would like to have more info. We'd want to kind of zoom in and say exactly where these charges are bunching up. Maybe not, again, we don't want to necessarily go back to having to say where each literal individual charge is. But again, I want to kind of zoom in enough that I can give enough detail to where the charges are that I can still get an accurate answer without having to kind of pinpoint each one down, to the umpteenth decimal spot. So you could imagine, right, that if we want to describe the charge distribution on more detail, then we essentially have to use smaller buckets. And if we go back up here, we notice that as we go to smaller and smaller buckets, then the amount of charge in each bucket decreases, right? All the charge is in a single bucket, but as I divide it up and up, each individual bucket has less and less charge. Or eventually it might be that there will be buckets with no charge or only a single charge when we get down to the finest resolutions. Nonetheless, this idea of a density can still be meaningful, that even though the numerator and the denominator might both be getting smaller as I go to smaller and smaller buckets, the ratio might converge to a answer. And if you know your calculus, that might sound like something, where you have something that's really small divided by something that's really small, and it becomes nonetheless a number. Here's another motivator. So suppose you had a true uniform distribution of Q over a rod of length L. So if your rod of length L, and it really is that the charges are uniformly spread out. Then, of course, over length L, there is a Q total charge, right? Over this entire length, there is Q charge within the bucket. But then if I cut it in half over L over 2, then that necessarily has half the charge, as in this bucket. So I've made the length smaller, and I've also made Q smaller. But then notice the ratio is still the same, right? It's still Q over L. If I make a bucket that's 1/100th as big, this bucket's too big to be that, but you can imagine 100 of these things. Then the length of that bucket is then 1/100th the original, and then there's 1/100th the charge in that bucket. Both of these numbers are starting to get smaller. If I have 100 million buckets, then each bucket is 100 millionth as big, and there's on average 100 millionth the charge in each one. So there might only be a little bit of charge in this very tiny, 100 millionth size bucket. But nonetheless, the charge density, the total charge divided by the total length, notice it's the same for all of these. Q divided by L, Q2 over L2 is still Q over L. This divided by this is still Q over L. This over this is Q over L. And if I were to make the bucket smaller and smaller and smaller, the way I might write this is I might write that over some bucket of size dl, there is dq worth of charge. And what these are coming to represent, which I'll iterate in the next couple of pages, is that this dl is representing a very, very tiny size bucket. Essentially, this is representing a very tiny amount of length. And this dq is representing an absurdly tiny amount of charge. As I make these things smaller and these things get smaller, they might become so small that I don't really care about specifying the exact value. But I'm just going to write dq and dl as representations of it's ungodly small. And if you don't think it's small enough, make it smaller. You just keep going and make it as small as you think is necessary. But then nonetheless, for this particular example at least, the charge density is still the same. Of course, eventually the buckets are too small and the individual charges, right, aren't in the bucket anymore. And that's kind of where this motivating analogy breaks down, because calculus will go as small as you want. But again, we can think of going so small that we're down to individual charges in the bucket, which is pretty small. I think, that we would be well within our rights to go switch over to this kind of calculus, limit in that case. So really how we will define the charge density is going to be defined as dq over dl. So you might recognize that as a derivative, right? dq over dl. And that is going to be the definition of the charge density. And again, the way we're interpreting this is that, again, if I think of the amount of charge that is on average spread out over a particular bucket, is that there is a tiny amount of charge smeared out within a very tiny bucket. Now that's probably different than kind of what you're thinking when you think of derivatives. And that's okay. We'll get back to that idea. But we're using these dq's and dl's representing a little bit of charge over a little bucket. Let's see, I've already talked about that. We can go beyond 1D and do 2D and 3D charge densities. Right? I might have charge distributed over a sheet of paper or a disk. Or I might have charge distributed over some sort of volume, something charged within a box. We can essentially define this in the same way. For the 1D, we had buckets of length L because it was a 1D problem, right? Charge over these kind of 1D buckets. You can imagine for the 2D, you instead of having kind of a 1D bucket, kind of have a 2D bucket, where charge can go in. And then for 3D, right, imagine, I can't really draw a 3D bucket in a 4D space, but you can imagine 3D buckets that charge could be within. Now, the way we define it is the 1D density is kind of a little bit, charge distributed over some length. Here it's charge over some area. And for 3D, it's charge over some volume. So I should specify that these are to the 2D and the 3D. So note that these all are definitions that involve derivatives. So I think now it's worth doing a reminder about what we really are thinking about when we think about derivatives. So if I had to ask you, based on what you know, if you were to describe what a derivative is, how would you do so? Well, if I had to take a guess, probably the first answer that would come, if I were to ask this in class, is that people would start talking about tangent lines or slopes. And derivatives are something about tangent lines and slopes. And that's indeed kind of one way of defining and thinking about derivative. That if I have some function f of x, I can look at essentially the slope at a point, by considering kind of 2 points that are successively closer to one another, such that I'm defining and thinking about the slope, essentially at an individual point. And the way it's usually thought of is that at that point, if I were to draw a tangent line, that tangent line would have a slope that is equal to what we call the derivative of the function at that point. So think of a slope, think of a tangent line, and then for all these I'm going to give in the red kind of maybe how we might try to level up our understanding, and ground it maybe with some kind of physics examples. So again, what this is saying is that the derivative has something to do with rates or instantaneous change. Right, so the definition of that v is the derivative of x with respect to t. Right, what is this saying? It's saying that velocity is how x changes with time, or how position changes with time. So these d's are essentially the calculus version of delta. When we write delta x, right, we consider that a change in x. But as I make the changes smaller and smaller and smaller, we replace that with a d. So don't think there's nothing really special about dx. Right, it's just essentially delta x, but it's gotten so absurdly small. Oops, and then I wrote y for some reason. That, and then it becomes a dx. So, another example, dn dt might be kind of how a population changes over time. So if n represents the population, dN by dt is how the population changes with time. Right, so how population changes, over some amount of time. And then other ideas that we know from Intro Physics 1. If I want to talk about kind of my total displacement, right? How much have I moved, say, in the y direction? Well, that is, if I'm moving at a constant speed, right, then that's just my velocity or my speed times delta t. Right? If I'm going 30 miles per hour and I travel for an hour, then I go 30 miles. If I'm going at 30 miles per hour and I travel for 3 hours, then I'm going 90 miles. And then since velocity is defined to be the derivative of my position, then this is saying that there's a connection between kind of my total displacement and a derivative of my displacement. All right, so in this case, right, your displacement is dy dt multiplied by this kind of delta t. And we'll come back to this because this gets into kind of the connection it has with integrals as well. Another way you might say a derivative is that you might say something about some limit of rise over run, right? So if it's slopes, we know slopes is kind of rise over run. And you might remember this kind of formal definition of a derivative, and that's all well and good, right? That's indeed the definition, the kind of limit definition of the derivative. But again, what is this talking about? This is talking about, again, how we can approximate slope as rise over run of a bunch of successively smaller triangles. And this idea works. Why does this work at all? Because again, it looks like the denominator is going to 0 because the x's cancel, and we're taking the limit as delta x goes to 0. Looks like I'm eventually dividing by 0. That seems like a bad thing. But again, it's the idea that the numerator also is going to 0, and you get this, but in the ratio converges to some finite number. And we'll let the math majors enjoy all the time they'll have in real analysis, their junior or senior year, proving these things. For now, we'll take it that people have already worked through this, and there's nothing kind of weird about this. But again, math aside, what intuitively is this telling us about, and why does this work, on kind of an intuitive sense? Well, if I think of that the derivative is a rise over run, right, I can think of that, dy dx. Now, if that's rise over run, then that's some kind of delta y over delta x, where these deltas are getting very, very small. And this is all possible because essentially if you do zoom in, any function more or less straightens out to become a nice straight line where the slope is well defined. Right? When I look at this thing, which kind of looks like a sine curve, I can't really meaningfully talk about the slope at this point. Or at least, my intuition has a hard time talking about the slope at this point because that doesn't look like a line. I don't know kind of what slope to use. But then if I zoom in, then this part here starts to straighten out a little bit, but still kind of curving. I can then take this little point and zoom in even more, and then it's really starting to straighten out. I can take that and zoom in even more, and then essentially if I zoom in enough, zooming in at that particular point, the function essentially does become a straight line. And then the slope is well defined. The rise over the run is an exact number that I can write down. And that, of course, and then we could keep zooming in, and that's the idea of the limit, right? That we could just keep zooming in. We never stop zooming in. And then, this converges to a well-defined number. So this is helpful in that we can, again, think of derivatives as kind of a change in y over a change in x. How things change, as a result of something else. And that's probably the kind of two basic, ways you have of thinking about derivatives. That's usually how they're kind of taught and introduced in a math course. I want to do a little bit more, and then I think this helps, again, kind of build an idea about what's going on conceptually. And if we think of this as, dy dx as delta y over delta x, that motivates how you might think about this kind of dq, or kind of like dy is. Because I think people see these dx's and dy's and dq's, and they think that there's some magic different thing that, essentially you don't know how to handle, and you get really uncomfortable when they appear in expressions because you don't know what you're allowed to do with them. What you might just start to think about is that, when I write a quantity dq, what that means is a little bit of q, a very tiny amount of q. dx, if x is a length, then dx is a tiny little bit of length. A nanometer on top of of length compared to a meter or something like that. If q is charge, right, then dq is a exceptionally tiny little bit of charge. Right? You don't necessarily have to always think about these things like derivatives as changes. Right? We can think of them as tiny little bits of tiny little quantities. So a little bit of q, a little bit of length. And then that may make it a little bit easier when you have to deal with quantities that depend on these little dq, on these deltas. So for example, I guess I'll write this in red as well. Right, if the electric field of a charge is kq over r squared, r hat, then if I have, say, a rod, and there's some point I'm curious about, right, and the electric field is going to be kind of the contribution from all the charges that are along this rod, then I might have a good amount of charge, but that's all being spread out so that I could break up this rod into a bunch of tiny little pieces, where in each of those cases there's going to be a little bit of charge, that's in each of these cases. And I'm writing dq for all of them, and that's okay. And that the dq is representing that there's a little bit of charge located there. And since a little bit of charge is since charge is what creates the electric field, then from this particular dq, right, I could measure, right, some r and some r hat and whatnot. And for that particular dq, I could write kind of k dq r hat over r squared. And that's the electric field, but I'm plugging in that little bit of charge that happens to be there. And so then we would write this as dE instead of just E, right? Again, it is the electric field that's resulting from this particular charge, but since it's a little bit of charge, then I just write this as dE, which you can think of as a little electric field, a little kind of E field contribution. Because Q is very small, since dQ is exceptionally small, then since it's in the numerator, then you expect dE to also be exceptionally small, for example. Right? Or I could write, for example, kind of d, the magnitude of E, is kind of k dQ over just r squared. Right? If I was just thinking about the magnitudes. In this case, then, and again, there's nothing really fancy about what this is that it's just a little bit, in that it's a quantity that depends on one of these kind of tiny little pieces. Right? There's a little bit of charge that creates an overall electric field, but since this depends on one of these tiny, kind of calculus, little pieces, we then write a d in front of this as well. So kind of a little bit of E, right, if you want to think of it like that. So then for things like this charge density, like when I say that lambda equals dq over dx, right, that's essentially saying that the density is saying about that there's some little amount of charge kind of smeared out or spread out over some small length. And that goes back, my penmanship was terrible there, apologies for that. So again, that goes back to the idea that, if I really want to define kind of where the charges are, I don't want a big bucket, but I want a ton of very small buckets, where in that case, each of those buckets is going to have ultimately a small amount of charge because I'm dividing everything up into very small, tiny, tiny little bins. And each of those bins has a small little length. Again, the D's are really only representing that this is kind of absurdly small, if you want to think of it that way. Let's see. So just, I guess, to give some quick numerical examples, right? If you had a uniform charge, right, where I said lambda is lambda naught, where lambda naught is 3 nanocoulombs per meter, then that's saying that, if I had a rod that was kind of 1 meter long, so 0 to 1, and I were to break the rod into, an absurdly small number of buckets, 10 to the 12 buckets or something like that, then in each of those buckets, I could look at how much, there'd be a little bit of charge in each bucket, over a small, little bit of length. But for a uniform charge, we essentially did that example, a couple pages ago. That's what we did here. That for a uniform charge, that even as we made the bucket smaller and smaller and smaller, both the numerator and the denominator got smaller, and would converge to the same answer. In this case, it would converge to 3 nanocoulombs per meter. Which again, 3 nanocoulombs per meter is saying that if the rod was 1 meter in length, then, if I counted everything up in all those tiny absurd buckets, all those small little bits of charge, I would ultimately have 3 nanocoulombs of charge. Right, so Q total would be 3 nanocoulombs, in this case, because there's 3 nanocoulombs distributed over 1 meter. In this case, it's written as uniform, so no matter kind of what length scales you look at, that's kind of the ratio you're always going to get. And again, saying something about how the charge is distributed, right? That no matter where you look on the rod, you see the same amount of charge everywhere, such that if you added it up over the entire rod, you would get a meter. Now what about this second example? So in this case, the charge distribution is lambda naught again, but then there's this function over here, this kind of 1 minus x squared over x naught, where x naught is a meter. You might think, well, if x naught is 1 meter, why am I bothering with this at all? Well, again, here's where I quibble, because a math class would probably just write it like this. To which I would say boo. Not because I have anything against math majors, right? I was a math major myself. But in that, the units, again, like we always have to be careful with the units, in a science class. If this is a charge density, this is a charge density. So unit-wise, like, the unit of this is the unit of this, which means this entire thing better be dimensionless. If I just write as 1 minus x squared, and then I'm plugging in, 1 meter for x, that seems confusing to me. Unless you tell me that kind of x must be in meters before you plug in a number or something like that. So usually, I prefer to kind of explicitly write it out like this. Because here I can say, okay, 1, that looks dimensionless because I didn't write a unit next to it. Here I have a length divided by length. Okay, so that entire thing is dimensionless. Square it, still dimensionless. This entire thing then is dimensionless. And so then all the units make sense. And then what does that look like, right, if I were to plot this, between kind of 0 and 1? And it seems like, it would just be a parabola that kind of goes down. When x became 1 meter, it would go down 0. Up here, that's where it would be kind of lambda naught. So in this case, if this is the plot of the charge density, it seems like the charge density is higher up here and then gets lower over here. So if I were to say, draw the rod and draw a bunch of charges, seeing what that's saying is that there's more charges over here, and then they become more and more spread out as you go that way, eventually going all the way down to 0. So the amount of charge decreases as you go to the right. In this case, it is not necessarily, actually it is not the case that if I were to say what is the total amount of charge on the rod, what is the total Q? It is not 3 nanocoulombs because it is not uniform like it was above, where here it was uniform, so we were saying with great accuracy 3 nanocoulombs are spread over 1 meter, since this was a constant. Here we have a function in that over on the left side, if I were to take this particular bucket and just replicate and replicate that bucket over and over again so that it was a straight line like this, then there would be 3 nanocoulombs per meter. But it doesn't do that. This bucket has more charge, but then this bucket has not as much charge. This bucket essentially has zero charge. So overall, I expect there to be less total charge on the rod compared to this case here. So that brings up another question. What is the total charge in this case? How could I figure out what the total charge is given the charge density? This is telling me how the charge is distributed, and presumably that is connected to the total charge. Well, if I think of this thing as buckets, then if I want to figure out the total charge on the rod, I should just sum up all the buckets. So if I have some rod, and I just look at the individual buckets, I could then just start counting the amount of charge that's in each bucket to give me the total charge on the rod. And again, the idea is I'm zooming in so that these buckets are ungodly small, and then adding them all up kind of brute force way. Such that if I were to say that each bucket has delta Qi on it, right? So that this bucket has delta Q1, this bucket has delta Q2, delta Q3, 4, 5, 6, etc. Then the total charge in this case is just going to be I add up all the buckets. Right? So it's just, adding up over the bucket, and then how much charge is in each bucket. Well, this is then, of course, what becomes, in calculus, what we call the integral. So the integral is nothing but a fancy adding machine. And why did I draw the S this way? Because S, right, for sum. Note that the integral essentially kind of looks like an S. And that is not coincidence, right? That is what Leibniz kind of was thinking by writing it down this way. So essentially, the integral itself is just a fancy way of doing sums. So when you think of, like we've likely seen before, of the total charge is you add up all the pieces. Essentially, the integral, the calculus version of it that says the exact same thing is this. And then when I have this integral dq, that just means add up all these tiny little bits. Because again, we're going to think of dq as a little bit of q. And this integral is going to represent kind of adding up, add or sum. I'm going to sum all the little bits. And that's going to give me the total charge. And again, the calculus version is that you have 10 to the 20 of these tiny little buckets. But then the integral gives you a way of doing that without having to count 10 to the 20 individual numbers. So then we could ask the same question of just, if I had to ask you to explain an integral, how would you explain an integral? Well, I would guess the first thing you would probably say is area under the curve. And that's all well and good, for a 1D function. And it helps us develop some intuition. But that can't be the only way we think about integrals. Right? So again, you probably recall that if I write the integral of f of x dx, between 0 and 3, then that is representing the area under this function between 0 and 3. And I'm going in the x direction. So another thing to point out is that whenever you have integrals, just how if I wrote sine, if I wrote sine of left parenthesis 3, and then I never wrote a right parenthesis, you would say, that's weird, something's wrong. Right? You never write sine of this without a this. Or you never write, logarithm of left parenthesis without a right parenthesis. Similarly, you never write an integral without a d something, right? So you can think of this kind of as like left parenthesis, right parenthesis. So there's always an integral, and then there's always a d something. And then The something is what you are kind of the dimension you're integrating over. So we're changing x. So as I go from 0 to 3, that's x goes from 0 to x goes to 3. I realize in our sophomore class that a lot of students did not appreciate this, that when you write kind of a 0 here, that 0 is an x value because that is what's after the d. This 3 is an x value because that's what's after the d. So something to keep in mind. So if I wrote, integral of f of x comma y dy, then this would be an integral over y. So if I did kind of 3, 4, this 3 and this 4 are y values. Anyway, where does this area idea come from? Well, it comes from the definition of the integral, the Riemann sum. And we don't necessarily need to get into that, other than conceptually kind of what was the idea here of the Riemann sum. The idea was that you were essentially taking this function and breaking it up into a bunch of rectangles. Because rectangles, I can calculate the area of each rectangle. And in this case, that starts to represent the area under the curve. But I'm kind of missing this piece. I'm kind of overshooting here and overshooting here. But you can imagine if in the limit that I make each of these things very, very small, let me make my buckets really small, then I also, as a result, have more and more of these things. Then each of the rectangles essentially starts to pretty well approximate the function. Because again, the function itself, essentially if I zoom in enough, becomes a straight line. Essentially if I zoom in, as the rectangles get thinner, eventually f of x, if I zoom in enough, x of x essentially becomes a constant over one of these rectangles. Obviously f of x is not a constant overall, but if I zoom in, and then zoom in more, and then zoom in more, each little piece of this line essentially is not changing over the width of the rectangle. And so, again, but why areas? Why, what, if I don't want to think of this in terms of areas, then kind of what else? How might I motivate this kind of with a physics idea? Well, I like to think of the idea of distance, right? I know that distance is velocity over time. That distance is velocity times time. If I go 60 miles per hour for an hour, I go 60 overall, etc. And that is a completely 100% accurate formula if v is a constant, right? If I'm accelerating the entire time, my v is changing, then which v do I plug in? Well, then you have to be more careful. But if I'm going at a constant speed, this is a completely accurate formula. So if I go back to this idea of rectangles, if I imagine breaking up my delta t's into a bunch of very, very tiny values, so that even if my velocity is changing, right, I can imagine I could make these delta t's so small that over this little small interval, I'm going at a constant speed. And then over this next small interval, maybe I'm going at a slightly different, but still constant speed. And so then each of these individually are completely accurate, because this is a completely accurate formula if v is a constant. So again, by making these rectangles small enough, then my velocity essentially becomes a constant over each rectangle individually, and then each of these is completely accurate, and then I just add them all up. And then that is what we then, of course, call the integral. So the integral of v dt is I'm just breaking up a bunch of I'm breaking into a bunch of small rectangles where my velocity is constant over each of them, and then my total displacement is accurately represented by this thing we call the integral. And then, of course, a math course then would geometrically kind of connect this, that this is, a height times a width. So this looks like, these are just a bunch of rectangles. So it's indeed an area. But again, what this is coming from is that, this kind of definition here is coming from these ideas of rectangles. And they are adding up a bunch of tiny little bits, which if we used kind of dq to mean a little bit of q, then presumably we're going to need a way to add up all those little bits. Of course, we saw above, what we do is that we represent that as an integral, as a way of adding up all these tiny little bits. And here the tiny little bits just happen to be, say, velocity times dt, right? A little bit of time and your velocity during that little bit of time. Okay. Then another way you would probably say it is, what's an integral? You would say something about an antiderivative. And that then, of course, gets into like the math calculation component of this thing, where, and this is slightly sloppy, but the idea that the derivative and the integral are inverses of one another. That's the fundamental theorem of calculus, which is not written like this. This is a sloppy version of it, but it has the idea of what I mean here, and that like if I take an integral, the derivative essentially and the integral cancel each other out. So the derivative of an integral kind of gets you back the function, and then the kind of integral of a derivative gets you back the function. So you can think of them as kind of inverses of one another. Just how like you have tan and arctan are inverses of one another, or square root and squaring are inverses of one another. X over 1 over x, etc. So again, kind of conceptually, right, the idea is that, this idea of antiderivatives is that, the integral of f of x dx is something we call capital F, the antiderivative. And how do I figure out what this is? I ask myself, what function would this be if when I take the derivative of it, I get back f? That's, again, essentially what this is saying, that the antiderivative, when I take its derivative, I get back the original function. And again, that's technique, just rules of integration and all that fun stuff. Thinking conceptually, again, the idea is that if I think of lambda as my charge density, so that it's dq dx, then by these ideas, I can think of, if I want to get back q, then I need to cancel out the derivative. How do I cancel out the derivative? I take an integral. So if I take an integral of this entire thing, then the integral of dq dx, the integral and the d will cancel, and I get back q. So this sort of idea also, of just kind of like how that the fact that these things are connected to one another. If derivatives are breaking things up into a bunch of tiny little bits, the integral is a way of adding up all those tiny little bits. Which then motivates the third version, again, of probably not what you are thinking of when you think of integrals, because this is not really what a math course would teach. But again, I would think of it as the sum of a bunch of little bits, where my third definition of the derivative was a little bit, the definition of a little bit, where an integral then is the sum of these little bits. And again, we get back to this idea of the total charge is, I'm going to add up all the charge in the buckets, but then I'm going to represent that as I'm going to add up or sum all these tiny little bits of charge. And I think this again kind of goes through the idea of displacement, but again thinking about this, which I think I ended up saying in the previous page, so I kind of already did this argument of so I'm not gonna repeat myself there. So this, I think, ends up being kind of very helpful in what we're about to do, right? And thinking about everything in terms of little bits. Not always thinking about derivatives as rates of changes or slopes, and not always thinking about integrals as areas. But but integrals are adding up little bits. Derivatives, right? You can think of as a little bit divided by a little bit. And this essentially gets us to what I call the physics faux pas that the mathematicians will roll their eyes at, because you actually need to more rigorously prove that you are allowed to do this, but it works, and we will continue to do it. And it's actually, the proof is actually not that hard that you can do stuff like this. In that, it's often very helpful for you to think of the derivative kind of as a fraction. The derivative is defined to be the limit of rise over run. But again, we kind of before said that I can think of the derivative as kind of approximately delta y over delta t, in this case. So you're thinking of it kind of as a fraction of two things. That can be helpful. For example, let me sketch this out rather than the answer just being there. That if I want to think of, say, if I know my kind of, how far have I traveled? I know that going to be I'm going to add up my velocity over time. I'm going to break my time into a bunch of little bits, because then I know over each one of those tiny little bits, every nanosecond, my speed is essentially a constant, and then I'm just adding up, v times delta t, for all those absurdly tiny little delta t's. If you want to think of this symbolically, well, the integral velocity is the definition of dy dt, for example, if we're using y as distance. So in this case, I'm just replacing v with its definition, right? It's the derivative of position. And here's the faux pas, in that the derivative is a thing. Like this is one entity. Like I could come up with a different symbol, like a capital D, and represent it as the derivative, instead of writing it as dy over dt. Or you come up, with some kind of fancy symbol that represents this. But it's usually written as dy dt, so it kind of looks like a fraction. And that's because, again, while this is a faux pas, but it works as long as you kind of know what you're doing, that if I do think of it like a fraction, then I can say, okay, well, the delta t's cancel. And then it seems like then this becomes an integral over just dy. But then I know, by what we've just been talking about, this just means add up a bunch of small little changes in my position. So if I add up all my little changes in position, then that's going to be, of course, my total change in position, which is indeed the case. But again, the mathematicians will roll their eyes as we think of the derivatives as fractions. But it generally works, and at least helps if you're trying to develop some feeling for kind of what's going on here. So again, that's the part that probably is worth a listen to at some point again. Let me do now some numerical examples, and then we can be done. So I think I have 3 numerical examples to walk through. So what is the total charge on a 1 meter rod if the charge density is 3 nanocoulombs per meter? And we already said that we think the answer should be 3 nanocoulombs. But again, it's always nice to have a problem that you know what the answer is supposed to be, because then I can check my work when I try to do it in this more kind of rigorous way. So there's the rod, and it has some charge density. And I want to know kind of what is Q, the total charge. Well, if I want to think of this rod having a bunch of little buckets, then I know then this rod has a bunch of tiny little buckets, and each of those little buckets has a little bit of dq, because the charge density has spread things out across this rod. In this case, it's evenly across the rod. But I know that if I make the bucket small enough, that each one of those buckets is going to have some little dq in it. So then the total charge, of course, is I'm just going to add up all the buckets. So by that means I'm going to do the integral of dq, which means just add up all the buckets, add up all the charge in the buckets. Now here's where the charge density comes in. Since charge density is defined as dq dx, and then that's just equal to lambda naught in this case, 3 nanocoulombs per meter. Then again, if I do my faux pas and think of this as a fraction, then it looks like dq is equal to lambda naught times dx. So in this case, again, a little bit of charge is the result of the charge density over a small bucket of length dx. Each of these buckets has some length. It's very small because I've broken this up into 10 to the 20 buckets. And there's going to be some small amount of charge in that small bucket, and that's going to depend on the charge density. If the charge density is high, there's going to be more charge in each of these tiny buckets. If it's small, it's going to be small. So then I can write Q, which was the integral of dq. Instead, I'm going to write it as lambda naught times dx. So now I've turned this, this is an integral, or kind of add up all the small charges. this is now kind of an integral over the buckets, right? So essentially you're adding whatever lambda naught is times the length of each of these buckets, which again, of course, dimensionally is the total amount of charge, right? Because we wrote this with an equal sign. And so if I wanted to write this as a definite integral, this first one I don't really know how to write as a definite integral. I could, but it would confuse things. Right, so there I'm adding up all the individual charges, and I'm saying that's the same thing as doing lambda naught dx. But I know that x goes from 0 to 1. So that's a meter rod. I'm going to put the origin kind of at one side of the rod, and it goes out to 1. So again, like I said before, this 0 is an x, this 1 is an x. And then it's just the machinery of antiderivatives. So which we can review, and I won't really review it right now, but the integral of this, lambda naught is just a constant, so I can take lambda naught out, so it's the integral of 0 to 1 dx. So then I might write that as lambda naught times x, and then I might write this as plus c, between 1 and 0. And remember the plus c is that constant of integration, which honestly I always, in a science class, I always make sure my integrals are definite integrals. So, which you might recall, this constant of integration doesn't matter if you have a definite integral, because you end up just subtracting it out, because then I take lambda naught and I plug in 1 plus c, and then I subtract from this lambda naught, but then I plug in 0 for x, and then that's plus c. And then notice, of course, the c's cancel, and it looks like I just get lambda naught times 1. Really, I should be careful. Even I'm being sloppy right now. Right? This is not just 0, it's 0 meters, 1 meter. So really, in this case, then it's lambda naught times 1 meter, which is key because this is 3 nanocoulombs per meter times 1 meter, and then the units cancel. Right? If I plugged in 100 centimeters, which is also a meter, well then the centimeters and the meter wouldn't cancel. I'd have to do a unit conversion. And so then this is just 3 times 1, right? 3 nanocoulombs. Huzzah. So when it's a definite integral, I'm not going to bother writing the plus c because they just go away. All right, what about this one? So here the density is non-uniform, but my desire is I want to add up all the charge. So I'm going to do some integral dq. But then I'm going to, again, use the fact that that lambda is dq dx. So dq is lambda dx. And then lambda in this case is lambda naught 1 minus x over x naught squared. And that's all with dx. So then it looks like this q is the integral of lambda naught times 1 minus x naught all squared dx. And then this is again a 1 meter rod, though I did not write that in the prompt, sorry. So going again from 0 to 1 meter. So then I have to take the antiderivative of this thing. And here's where we have to make sure we were being careful. You might remember the antiderivative of x squared is x cubed over 3, but then that x naught squared is a constant, so I just have to make sure I'm careful. So if I'm going to write this out, right, this looks like it's the integral from 0 to 1 of lambda naught dx minus the integral from 0 to 1 of, and I'll break this apart, 1 over x naught squared times x squared dx, and I lost the lambda, so there's also lambda naught here as well. I just multiply things out. Because then it becomes clear, because we're constants, right, this is between 0 and 1 of lambda dx, so that looks like it's just then lambda naught x, between 1 and 0, minus, then lambda naught 1 over x naught squared is a constant, then that becomes, looks like 1/3 x cubed between 1 and 0 as well. And again, plus c's, but I don't care because they're definite integrals. Now, I won't belabor this, but we could, I'll leave it as an exercise. You can also make sure dimensionally this better makes sense. Dimensionally, this is charge, but then this is charge per length times a length. Okay, so that checks. But then what's going on here? I have a charge per length divided by length squared. Okay, so it seems like that's a charge per length cubed. But then I'm multiplying by a length cubed. So then this ultimately is also just charge. Very good. And then you plug in numbers and you do all that, and I believe you get 2 nanocoulombs in this case. So in this case then, the total charge is not 3 nanocoulombs, but it's 2 nanocoulombs. It's 2 nanocoulombs. And that's because as you go to the right, the charge density was decreasing. And then, real quick, if you have a 1 centimeter radius disk with 2D charge density given by sigma equals 4 nanocoulombs per meter squared, what is the total charge? Again, I'm trying to do, my total charge means I'm going to add up the little bits of charge that are now spread across this disk. Right, so, since charge density is per area, I can imagine instead of a bunch of 1D buckets, right, I can imagine breaking this up into a bunch of little 2D buckets. Each one of those little grid cells has some charge on it, such that sigma is defined to be dq d area, where each of these buckets has some little area. So that looks like dq is sigma dA. So then this is the integral of sigma dA. But then the sigma itself is just a constant. I should have given it a symbol. Let's call this lambda or sigma naught. So then that's just sigma naught, integral of dA. So again, I am adding up a bunch of little areas. So just by this alone, conceptually, if I'm adding up all these little areas, I'm going to, of course, get the total area of the disk. So then that should be sigma times pi r squared, which then you can plug in numbers. 4 nanocoulombs per meter squared times pi times, then we've got to make sure, right, since it's meter squared, I don't plug in 1 centimeter squared, but I'll plug in 10 to the minus 2 meters squared. The meter squared cancel, and it looks like I get 4 pi times 10 to the minus 4 nanocoulombs in that case. So, again, notice the heavy lifting here is being done conceptually. It's not that I'm just looking for what's the formula for this antiderivative. I'm thinking conceptually about what the hell I'm doing in terms of adding things up, or thinking about things, or thinking about these little d's, dq's, and dx's, and dm's as little bits. And so these expressions like this, are a little bit, little thing over little thing smeared over a little thing in terms of density. And of course, it can also represent changes, and slopes and stuff like that. But, okay. So then we're going to take this, and we're going to take these charge distributions, like lines and disks and rings, and calculate the E fields. And so here it's going to be key that if we know that the charges are distributed, as a bunch of little bits, then we're going to use something like this to then create, from each one of these little bits of charge that creates an E field, and then we're essentially going to want to add them all up and to get the total E field. So then we're going to ultimately have to do integrals, of this entire thing, which won't be too painful, only a little painful. All right.